We'll illustrate with an application, compression of images. Say you want to store or transmit some large images. How do we represent the image compactly so it's more efficiently stored or transmitted? One obvious representation of an image, a 2 megapixel image, is to represent each pixel by a number. And that's straightforward. Can we do any better? One idea, this is be our strategy one, is to use sparsity. So we find the nearest k-sparse vector. We'll talk later about what it means to be the nearest k-sparse vector. For now, I'll say that the method for doing that involves suppressing all but the largest k entries. Well, here's the result. It's not a very good reproduction of the original image. You lose a lot of detail by suppressing all but, say, the top 10% of the pixels. Are there better strategies that we can use? Here's another idea. We represent an image vector by its coordinate representation with respect to some set of generators. So we select a set of generators, say v1 through vn, and we replace each image vector with its coordinate representation. Now, for this strategy to be useful, we need to ensure, first of all, that every image vector is a linear combination of the vectors v1 through vn. So more generally, this is the question, how can we tell, given some vectors v1 through vn, whether every vector can be written as a linear combination of these vectors? How do we tell whether these vectors are in fact generators? We also need the number of vectors to be small, because that way the number of entries in the coordinate representation will be small. This raises the question, how can we find a smallest possible set of generators for the vector space? It turns out that that strategy doesn't work well either. You can't get a small enough set of vectors that still generate the whole space. But here's a third strategy that works quite well. As before, we select some vectors that span the whole vector space. For each image to compress, we view it as a vector, and we find its coordinate representation in terms of these generators. Now, we replace that coordinate representation with another vector that's k-sparse. Again, we suppress all but the k largest entries. We'll call that u tilde. And the compact representation is the vector u tilde. It's compact because it's sparse, so we only need to store the non-zero entries. Now, once we need to recover an image, we can do that by calculating the corresponding linear combination of the generators. Of course, the resulting image won't be identical to the original image, but it actually looks quite good. So here's the image we obtained using that first strategy, just suppressing the pixels whose values were not among the k largest. And here's the result of using this hybrid strategy I've just described.